Last week we talked about the two kinds of energy being kinetic energy and potential energy. Kinetic energy is the energy of motion. Anything that's moving has kinetic energy, and its energy was equal to 1/2 mv squared. 1/2 of the mass times the speed squared. Measured in joules, energy was a scalar. Then we talked about potential energy, and there was lots of different kinds of potential energy. The first kind that we had was gravitational potential energy, the energy stored due to an object's height above something, measured relative to something else. So, for instance, the energy of this pen relative to my hand is 0, because the height of the pen relative to my hand is 0. But the relative to the ground is something, because its height above the ground is something. We also talked about elastic and spring potential energy, briefly. Today we're going to focus on that one, spring/elastic potential energy. When we stretch an elastic back and let it go, it flings forward. Why? Well, because when we stretch it back, we store energy in it. If it's going to have kinetic energy in just a minute, when I let the elastic go, then it must have potential energy when I've got it stretched. You don't get kinetic energy from nothing. You get kinetic energy from potential. So the kind of energy that we have when the elastic is stretched back or when the spring is squished or stretched, we call elastic or spring potential energy. The more it's stretched, the more it's squished, the more potential energy we have. The stiffer the elastic is or the spring is, the more potential energy that we have. The equation that describes elastic potential energy is a new one for you. Unlike the last two, kinetic energy and gravitational potential. You'd seen those in physics or in Science 10. Elastic or spring potential energy is 1/2 times K times X squared. Now, what do all those variables mean? EP is the potential energy, the spring or elastic potential energy. Remember, it doesn't have to be a spring or an elastic per se, but just act like a spring or an elastic. In about a month, in just over a month, we're going to do our Physics of Amusement Park field trip to West Edmonton Mall. One of the rides that you're going to take data for is going to be the bumper cars. And one of the questions in the analysis booklet is going to talk about why there's rubber bumpers on the bumper cars, right? You guys know that there's rubber bumpers on the bumper cars, and intuitively we know that they have to have that, right? Why? Why do we have to have rubber bumper cars? That's the question, right? To absorb the shock. Yes, to absorb the shock. But the analysis question in the booklet is going to say specifically, don't use vague terms like shock. That's a good answer right now. Okay? But after we've gone through elastic potential energy, that's not such a good answer. Elastic potential energy is the energy that's stored in this elastic or something like an elastic that's compressed or stretched. When you hit a bumper car that has rubber bumper, then it squishes that, right? It converts the kinetic energy into elastic potential. And what does that do? Well, it absorbs the shock, right? It absorbs the shock when we do that. And then, of course, as it goes back to its normal state, what happens to the car? It gets propelled backwards again, right? It goes back the way it came. But if there's not squishy bumpers, not rubber bumpers, then you don't have any conversion from kinetic to potential. It just stays kinetic, and you bounce off really, really quickly. And you get a lot more shock then, a lot more force. Yeah. Spring or elastic potential energy is stored in elastics, springs, rubber bumpers of bumper cars, and things like that. X stands for a variable that we call displacement. The units would be meters. But it's not the displacement that you're thinking of. We have Jazz's elastic here. When I stretch the elastic back, okay, we know that it has potential energy because we know that when I let it go, it moves forward, right? Potential energy is converted to kinetic energy. There are two displacements that this elastic can experience. There's the displacement that we've dealt with up until now for the last 2.5 months. There's the displacement of the elastic moving, right? The change in position of the elastic. from here to the other side of the room where the elastic just went. That's the first displacement, right? Delta D. That's not the displacement we're talking about here in this equation. The displacement we're talking about here is how far it's stretched or compressed. Okay, right now, it's not stretched or compressed. When I pull it back 5 centimeters, it's stretched 5 centimeters. That's the displacement we're talking about. Not how far it's gone, its change in position, but rather how much it's stretched or compressed. Does that make sense? We'll just put a little note there. The amount stretched or compressed. When the bumper car hits another bumper car, the bumper on each of those cars isn't going to compress very much, maybe a centimeter or two, right? That's the displacement, the amount that the bumper is compressed when it hits another bumper. Okay? Not how far the bumper car is traveling to hit the other one, but how much the bumper compresses as it hits it. Now, K is even a little bit more tricky than the displacement. K is something that we call the spring constant. The unit for the spring constant, by the way, are going to be newtons per meter. And the spring constant is effectively a measure of how stiff the spring is, or how stiff the elastic is. You guys know from pulling different elastics, stretching different elastics, that some of them are a lot stiffer than others. Some springs are much stiffer than others, right? You go to compress the spring in a pen versus the spring in a car. The spring in a car is much, much, much stiffer. It has a much, much, much higher spring constant. Therefore, it has the ability to hold much, much, much more elastic or spring potential energy. That make sense? Now, every spring has a different value of spring constant. It can range from very small numbers, single digits, to hundreds, or even higher. Sometimes you're given the value of that spring constant. You know, if you get a big spring constant, then it's a stiff spring. You know, if you get a small one, it's not a stiff spring. Sometimes we're not given that value. Sometimes we've got to find the value of the spring constant. We're going to use something called Hooke's law to do that. Hooke's law provides for us a relationship between the force that's applied on a spring or elastic and the displacement of the spring or elastic. So F is the force applied on the spring or the elastic. And that's going to be measured in newtons, as force always is. X stands for, same thing as it did up here, it's the displacement, the amount the spring is compressed or stretched in meters. And of course, K is the spring constant again. So most times you get one of these problems, you're going to say EP is equal to 1/2 kx squared, and you're going to solve for whatever you need to find. Sometimes you need to find K first to plug into that equation. If that's the case, go to Hooke's law, get K, and then plug that value of K up into here into my potential energy equation. And then go from there. So let's take a look at an example on page 301. Example 6.4. It says a spring is stretched to a position 35 centimeters from its equilibrium position. Equilibrium position is its natural position, the position it is if it's just sitting on a desk. It's stretched 35 centimeters from that equilibrium position. What variable is it that we're given? Right there. If it's stretched to 35 centimeters, by the way, first I want to circle that centimeters because that's a non-standard unit that I know I'm going to have to convert. I want to draw my attention to that so I don't forget to do that. What's this 35 centimeter deal there? What variable is it? Stretched that far. We just talked about that, right? Joe? It's a displacement. It's X displacement, not delta D displacement. Delta D would be Listen, if I threw the spring across the room, how far did it go across the room? That would be delta D displacement. The force exerted is 10.5 newtons. We want to find the elastic potential energy there. We'll worry about B later on. If the spring's allowed to stretch 20 centimeters. Okay, we want to find elastic potential energy. We know that we're going to say EP is equal to 1/2 kx squared. 1/2 times K times 0.350 squared. The only problem is I don't know what K is. I don't know what the spring constant is. I don't know how stiff this spring is. The amount of potential energy that the spring can store depends upon which spring it is. We need to know the properties of that spring. We need to know how stiff it is. We need to know what K is. How are we going to find it? Hooke's law. Hooke's law. F is equal to Kx, or K is equal to F over X. It's just a rearranged form of Hooke's law. We know what F is. It's 10.5 newtons. And we know what X is. It's 0.350 meters. I believe that's 30. Is that right? Somebody check that. 30 newtons per meter. Now I can plug that in here. 30 newtons per meter times 0.350 squared. And I can get the elastic potential energy there. Let's say 0.5 times 30 times 0.35 squared gives me an energy of 1.8375, which we're going to round to 3 digits, right? 3 digits, 3 digits. Final answer should be 1.84 joules. It's question A. B says, that was A, not B. B says, if we stretch it now to 20 centimeters, what's the change in elastic potential energy? Well, let's find the new potential energy. EP is equal to 1/2 kx squared. K is 30. Wait a second, is it still 30? If we wanted to find K now, wouldn't we say it's 10.5 divided by 0.2? Doesn't it? No? Why not? Yes, the force that we would apply would be less as well. If X changes, then F changes as well. Bottom line is this. It's the same spring, right? If it's the same spring, then it's got to be the same spring constant. So if we found it before 30 newtons per meter, then it's still 30 newtons per meter. Now the difference is that X is 0.20 meters instead of 0.35 meters. Let's figure out what that is now. Say 0.5 times 30 times 0.2 squared. It's 0.6 joules. Final answer? Almost, almost. What are we actually looking for here? Not the final potential. Austin, what are we looking for there? Well, you should sit somewhere where you can see it then. We can switch it. What are we looking for here? Let's see here. Kate, what are we looking for here? Not the final potential, but it's close. Looking for the change, right? Looking for the change in potential. So if we're looking for change in potential, delta E is the final minus the initial. 0.600 minus 1.8375 gives me negative 1.2375, or negative 1.24 joules. We said that energy is a scalar. What does a negative mean with a scalar? Usually means left, right? But in this case, heavy means it's lost, right? We lost 1.24 joules of potential energy, right? Oh, we got 5 questions here. Goodness, usually we only have 2 practice problems. This time we have 5. What I'd like you to do is have a look at those 5 practice problems, guys. We'll see where we are for time at the end of that, and then we'll either do one more example or we'll just do a little outline for your test tomorrow at the end of that. Okay, so take a look, ask me some questions if you have them, and then we'll go from there.